Good evening, everybody. Welcome to League of Extraordinary Inventors. I'm your host, Mike from Faraday Research. We have our usual panel. It is July 12th, 2024. Welcome to the show. We got Philip in Montreal, we got Lulu in Houston, and we got Mike here. I'm going to bring him on now from Florida. Everybody, welcome to the show. I hope everybody had a good week, other than Lulu. Poor Lulu just survived a hurricane, and she's kind of doing the show from her car tonight because she doesn't have power. So yeah, she's a real trooper, and she's with us tonight, safe and sound, thank God.
God.
And yeah, so welcome everybody. A lot of stuff on the go. Been doing a huge amount of research on these battery power cell stuff. I'm kind of under a disclosure right now, so I can't really talk too much about it. But I've been doing nothing but research. I got some parts on order. I got stuff coming in. Hopefully tomorrow I'll start my first batch of test batteries. And yeah, so I'll be disclosing stuff little by little. Probably, if I do, it'll probably be in Patreon, not on the actual Faraday Research YouTube channel, but it will be in the Patreon, little by little as we go. I'm under kind of a disclosure, so what I can share, I will. Some stuff, obviously, I can't. But yeah, but we'll get into it. I think Bernie just is in the live chat right now. Yeah, it seems like everybody's tired. I've had a busy week. Bernie's had a busy week. Everybody's had a busy week. But we'll plug through this, and I guess we'll start with Philip. What's happening with you and your projects? And I know you were doing trying to get some funding going at one of the universities. Maybe you can
Uh,
give us a little update on that.
yeah, I'm trying to get funding actually as fast as possible because I want to get my experiment going at the local university,
Yeah.
and I'm working on that. And there's I might have I might have some return of investment with some military affiliated project
Oh wow.
I'm working on, so I can't really
Yeah, you got.
make this public, but. Um, So it might be well over what I'm looking for, but I don't know the time frame for that. I hope it's gonna come in as fast as possible, but I'm not sure. So
Yeah.
yeah, so I'm working on that. So I spent a couple of all nighters this week working on this project specifically to speed things up because we need to make a demo next week.
Right.
So
That's cool. That's really
yeah,
cool.
yeah, I wish I could talk about it because it's really awesome.
I understand. I totally get it. So you got to do what you got to do to go forward with it down the road. Maybe you can disclose some stuff. It's entirely up to I guess what your agreements are and your disclosures.
Yeah, it's
That's
some sort of
that's yeah. That's just the way it is, right? In the science community, there's always some kind of disclosure agreements on stuff that's actually going into real science in real universities or military institutions or whatever. But yeah, when you get to that level, yeah, you're gonna have to sign some disclosures for sure.
but
So,
there's also a NATO project I'm applying for that might get funding within 60 days actually.
well, I'm NATO certified, so if you need somebody to work for you, I can do it.
Oh
I'm
yeah,
NATO certified in Canada, well, actually internationally. So
I didn't
with
know that.
yeah, I got that paper. Yeah, to get this job, the job I'm at right now, I had to get NATO certification and background check. That took 3 weeks to get all that done. And I had three private parties from other countries do background checks on me that are related to my work, but that's about as far as I can really
But
talk about that.
yeah, check it out. I just posted the link on the chat, the private chat.
Oh, okay.
It's there's a whole bunch of challenges. Maybe you would fit in the energy one, and I'm applying for the energy
Right.
one as well.
Yep. That's cool. Really cool.
It's called Diana NATO International.
Yeah. Yeah, I've got my federal certification license. It's actual federal paper, and I got a registered number for NATO certification.
Oh,
So,
nice.
so any third-party military contractor, I can work for them.
Oh,
So,
that's cool.
so with that paper, say I leave this job that I'm at now, I could go to another third-party NATO institution, and this paper will actually fast-track me through the screening process, so I could actually get the job like on the spot. So
Oh, nice.
yeah, so I have to keep that in a safe place, like anything else, put it in a lockbox, and then if I need to pull it out and use it. So I can work at aerospace, anything military, anything with high security clearance. Classified 2 levels under top secret, so it's pretty high clearance I have. So yeah,
Nice.
it comes in handy. It comes in handy, if you want to get work, right?
Yeah, that's
So,
awesome.
yeah.
There's also a link I just posted in the. It's
In the
some
regular
guy
chat.
that has some over Unity energy. He claims I didn't fully read the his website, but it's
It's in the private chat, you said? Or
yeah it's the
Today
second link.
Green Living? Oh, the
Today's
second
green
one?
link. No, the sorry the
Today
first one.
Green.
Yeah,
Okay, I'll definitely check
he's
that out.
commercializing his over Unity technology. So I didn't spend time really understanding. There's a lot of marketing here, but
All right, I'll check it out. I'm bookmarking it now, and I'll definitely check it out later in the show or later this week. I'll definitely check it out. I'm always into seeing what other people are doing, because that obviously is going to spark ideas. Yeah. So that's how it's done. I'm not biased, towards free energy or the new energy movement. I always look at what other people have to offer and their theories and different perspectives. And, if I can take a piece of what they're doing and implement it into what I'm doing, well, then everybody wins, right?
yeah. I saw also Gerald posted his experiment earlier
Oh,
this
right.
week.
Yes, I seen that too. Yep. He did the Gerard Morin device. It's a short video, but he did spin up a washing machine pump motor.
Yeah,
And yeah, I've seen that. So yeah, it works. It definitely works. It's what you put after the pumps that really counts, because like I can take that pump, I can spin it up and actually touch the leads coming off that pump motor. I don't get electrocuted. But the second you put it into a capacitor and then say through a transformer of some kind, then it becomes lethal. So obviously there's it's creating a vibration in the ether that basically starts pumping in the electricity into the transformer circuit and becomes what we call real electricity, real power, right?
okay.
So yeah, it's definitely a different concept. A lot of people try to debunk it and say, "Oh, it's not over Unity," but they have to understand the concept of what he is doing. It's a different method of creating electricity, other than it's more of a dynamo type thing. So it's hard to explain. You have to experience it. Like for the first time, if you spin that motor up and you put your finger on the leads, you technically should be getting electrocuted, because it's like 113 volts, right, coming out of the pump. But you don't feel a thing. I could wet my fingers and put it on the leads, and I don't get shocked. But the second I put it in a transformer, everything changes.
Yeah,
The whole dynamics of the power changes. So what's going on in that pump? How is it drawing that power? Is it a frequency? Is it harmonic? combination of both,
Right.
So that's kind of where he went off on, right?
Yeah.
You were going to say something, Mike?
Yeah, I'm a little familiar with the Gerard device. The transformer steps down the voltage.
No, it's stepping up. So I took the smallest microwave oven I could find, and I pulled out the transformer. So it's a 700 watt. So I take the leads from the pump, I put it into an AC motor capacitor. It's only, I think, 100 microfarads, something like that, small. And then from there, I put it into the primary of the microwave oven transformer, and then I extract the power off the secondary. And then you could either put it in another cap or whatever. But I'm getting about 113 volts at 0.433 amps.
So after you step it up, that's when you feel the zap.
Oh yeah, you don't want to. That's lethal at that point. You don't want to touch it after the transformer.
Yeah, because you're starting with 12 volts.
Well, the 12 volts spins the motor, which
Right.
spins the pump motor. You're not putting power into the motor. You're putting mechanical motion into that pump. So you're spinning the stator, right?
And do you know what frequency you're spinning at?
It says it's 60 hertz.
You're spinning at 60 RPMs or something like that?
Yeah, I have to regulate the power. It has a sweet spot, so it does. Actually, it doesn't take much power to do it. See, everybody will wind that motor out, but that's where the frequency changes. Now you're getting into high frequency. I try to home in on the 60 hertz, which means my motor's hardly spinning. It's spinning it, but not very fast. So just when I get it at 60 hertz, then I put it into the transformer, bump up the power. I'm getting 113 volts at almost a half an amp.
At 60 hertz.
At 60 hertz. So, yeah, it's definitely something to tinker with. Definitely something to tinker with for sure. But here's where it gets more interesting. You can wind the motor right out so it's spinning way higher and way higher frequency. So now you can put it into a real high step up transformer. Instead of getting hundreds of volts, you might be able to get into the kilovolt range, which Gerard Morin showed on a number of occasions in his videos. He was able to, I think he was getting about 3 kilovolts coming out of his ionizing transformer. So it's a real high step up, high voltage transformer.
What's it going to power with 3 kilovolts?
Well, he's showing the concept of how the power is different. It's based on the harmonic frequency resonance, and that's, he says, is what's happening in that motor. It's creating a resonance by spinning a magnet in a stator with a coil, and you're not actually pumping any power into it. It's only mechanical motion, right? So it's running like a dynamo. Now,
so he's going to drive a wheel with those kilovolts, or
he can drive whatever he wants. He can pump that now into an industrial size transformer. The ones hanging on the pole outside. So he hooked up his device to one of those huge transformers, and you can power a huge amount of devices. Now, obviously, the washing machine pump motor is very small. If now you can scale that motor up using the same principle as that motor, now you're getting into the kilovolt range of power, right? So he showed how those huge transformers can be actually run by a small little pump motor. It all has to do with resonance that you create with that motor.
Oh, right. Those huge transformers, they have inductive reactance, they have capacitance.
Right. They got everything.
They can charge up over time. So that little motor, let it run for a few minutes on one of those big transformers.
It'll build up inside.
It'll fill it up, right?
It'll fill it up, exactly. Yep. And that's what he was trying to show everybody. And nobody got it. 9 times out of 10.
As long as you're not loading it.
You can load it to a point. You can load it to a point, but obviously you're going to need a bigger version of that pump motor. So, and that's what he was working on.
So he's trying to use those huge transformers to act like a a power storage device instead of people using batteries.
Yeah, it would be like basically like power on demand. So he got into using the drum motors that you get out of front loader washing machines.
Yeah.
So he was in the midst of building a power unit that would power it at say like 400 volts, but almost no current. But those drum motors had a huge amount of torque behind them. So now he could spin a real serious generator with it, right? So his biggest hurdle at that time was getting the right controller made, and he was spent
What, to
a lot
handle
of
the high
time
voltage?
to put out that high voltage and be efficient, right?
Okay, yeah, you can't. I just came to a realization today that is similar to what we're talking about here, a similar category. You can't use a transistor to do what you're talking about here. It has
No,
to be a mechanical,
that's right.
you know,
Now this goes back in history.
because of the high voltage. You have
Right.
to use some mechanical switch.
That's right. Now, if you go back in history in the early
And if you
1920s,
want to do mechanical switching like that, you're going to need more than one switch on a rotor.
oh yeah,
Like
we're talking major power here. We're not talking benchtop work here. We're talking industrial stuff. But to go back in history, Charles Proteus Steinmetz made a similar device that was actually in operation in the early 20s. It was called the dynamotor, which is basically a ginormous version of what the Gerard Morin device is. Now, that motor was a free energy device because the grid was so big and had so much power in it, he could actually tap off the mains and direct that power and keep the coils energized and actually have that motor self-running off the system that it's sustaining. So that motor there was a free energy device. In real life, it stood about 12 feet off the ground and weighed about 30 tons. So we're talking some major hardware here. So anybody wants to look that up, it's called the Steinmetz Dynamotor. There are pictures of it on. I found them on Google. There is pictures and actually shows somebody standing beside it, and you'll see the scale of it. It's quite large. But eventually they got rid of it. I don't know why. Just they start going in a different direction. I know he had patents on it. He had over, I think, 400 patents to his name before he passed away. So he was the lead engineer for GE back in the early 1900s and early 20s. He did pass away in 1929. Charles Proteus Steinmetz, if you look him up, he was a dwarf, and he had a severe deformity of his back. You can see how he stood kind of really weird in pictures. But he did know Tesla. He knew some of the biggest names. He knew Einstein, all those guys. But he was really I'd say the big brainchild, other than Tesla. So whatever Tesla made, Steinmetz pretty much perfected it with the mathematics and also the engineering behind it. So he made it engineered to the point where you could use it in industry. So Tesla was more the free-minded creator of these devices, where Steinmetz was the guy who perfected the stuff. So Tesla and Steinmetz worked hand in hand very well throughout.
Tesla was pretty
20s.
perfect with his diagrams. If you look at them,
no, they were good, but Steinmetz did the mathematics to back all this stuff up.
Right.
So eventually, you probably know this term.
You mean the mathematics that regular people understood, not the mathematics that Tesla understood.
Right, but don't discount Tesla. He was an engineer. He was a very well educated engineer. Yes. So.
See, the Western engineering is running off of not running off a metric, for one.
Yeah, you ever heard of the Steinmetz method? That's his mathematics, I guess, for the power transmission. That's what really kind of propelled us into the modern age with long distance power transmission on lines. So he developed a lot of that stuff. He had, like I said, he had like 400 patents to his name before he died. So
But Tesla was clearly smart, but was did he finish his degree or?
yeah, he did. He did. He was at, I believe, the University of Austria, and I believe Budapest. And one of them he dropped out because he kind of went cuckoo for a little while, kind of went off the path, and then he got back in and finished his degree, and then he was working for some telegraph company, I believe, in Hungary, or sorry, in France, in Paris, and that's when he got the invite to go to the U.S. and work for Edison because he was working for the Edison Telegraph Company in Paris. So he got the invite for that, or his boss basically gave a good recommendation to Edison in the U.S. that Tesla would be a great fit for him to go there and work for him.
Oh, okay.
So that's when Tesla decided to hop on the boat and go.
Yeah.
That's when he came to America. So
I guess you didn't have to have a complete degree to get a green card back then.
well, he had a recommendation to work for Edison. So when he was crossing the border, he gave this note of recommendation for Edison. And that was basically what got him into the country. They were going to send him back because somebody stole his money on board the ship on the way down.
Oh yeah.
So he basically was like going on, across the border with almost no money in his pocket, just a few cents.
Wow.
But it was that letter that saved him. So he managed to get in.
Oh
So, yeah.
So, Mike, who wrote the formula for frequency?
Formula for frequency? Well,
Yeah.
well,
I thought it was
Hertz.
Tesla, no?
Well, Tesla was the real creator of it, and then Hertz came along.
And they started adding to it, right?
Yeah, they kind of built on what Tesla did, but
Right. He kept it simple though, Tesla. He had just like a few
I'm trying to
variables.
remember Hertz's first name. Heinrich Hertz? Heinrich? I think it was. Don't
Yeah, that's
quote me
right.
on that. Heinrich Hertz, yeah. But you have to understand, Tesla wasn't the only guy working on this stuff back in the day. There were a lot of engineers back there. Back in those days in Europe and Britain, especially out of Oxford, there were a lot of guys doing work. So there was a lot of times that Tesla got in some pretty interesting debates while he was doing his presentations at Oxford, and basically in the same building where Michael Faraday did his lectures. Tesla was getting grilled on some of the stuff because he definitely had some
Wait.
people that
Faraday was alive during Tesla's time? Or
no
alive?
he was doing his lectures in the same room.
Oh, the same room. Okay.
Yeah, the same auditorium. So I know he did several presentations at Oxford. So not only there, all over the states, and I imagine I think he even did some in Paris as well. There are a lot of engineers in Paris that were working on stuff as well. So yeah, there was a lot going on back then, right? Not just Tesla. But the problem is they were all involved in the same shenanigans that goes on today. A lot of backstabbing, a lot of patent stealing, a lot of patent wars, a lot of court battles, which Tesla was obviously a giant target, right? Even when Marconi came around with his radio, Tesla says, well, let him do what he's doing. He's already using 14 of my patents, right? So it's like, well, he's saying to himself, yeah, go ahead, do what you're doing, but don't forget about me here. I want a bit of the piece of the pie when you're done, right? So yeah, that sparked a lot of controversy, a lot of patent wars, and everything, right? So when they started to build the first radio transmission facility in Bolinas, California, which back then everybody knew as RCA, Radio Corporation of America, you had you had Marconi there, and then you had the Swiss guy. What's his name? Oh, it's on the tip of my tongue. He was the one that designed the antenna array. So yeah, those two were working on it, and then Tesla was in there a bit too, doing collaboration. But there was a lot of
Was
stuff
he with the
going on.
parabolic? No, that's
No, it's a very unique antenna array, like massive. See, Marconi and the guy that was working with them, they had to figure out how to create a radio system to circumvent the Tesla patents, and that was extremely important because they wanted to get Tesla out. They wanted to push him aside. So
That's
they had to
terrible.
come up with a new method. Yeah. So they came up with this huge generator system. It was, obviously in Hertzian, where Tesla's stuff was all scalar. All right. So the entire system had to be totally re-engineered to circumvent all the Tesla patents to keep Tesla out. So that was a big undertaking. We spent millions and millions of dollars on that project. So
Well,
yeah, a lot about.
Tesla's it was a vision. The other ones were all about the money. So it will never.
Yeah. He was the creative mind. He was the one who wanted to get the concepts into the world, where everybody else was worried about the bottom dollar in the end, and just created a complete circus of the whole thing. So the patent wars were going on crazy back then.
When money is put into an equation,
money.
Yeah,
All about the money.
Well,
it's called FOMO. The fear of missing out.
But you know what? The thing is
powerful.
That
it's like winning the lotto. Like.
I mean, imagine at his time was allowed, introduce, energy. We would have a different world.
Yeah, but the powers to be didn't want that. See, at that time, that's when the J.P. Morgan, they found the oil in the Middle East, and they wanted to go in a different direction. And as soon as he found out what the Wardenclyffe Tower was all about, and said, well, if I can't put a meter on it,
power grids today,
Yeah, like it's no different today. It's like their philosophy is if they can't put a meter on it, we don't want it. It's all about the money in the end. The corporations, the shareholders.
They don't want to market it anyway.
Yeah, that's a little bit why I enjoy working with the military or military related companies, because they're more focused, the best technology oriented, not necessarily the best money making
right
stuff, And,
yeah, I get that, but the problem is we're in a situation now where our society cannot keep going down the track we're going. There has to be a shift, and if we don't do it soon, having power outages on a regular basis is going to be way too common.
You got a lot of people that rely on machines to keep them alive, dude.
Right, exactly. Like hospitals, you're on a ventilator, you're on life support. You lose power, well, you're going to meet your maker really soon.
Oh yeah, I forgot to say that, but it's pretty easy to, Tesla's dream was to teleport energy,
right,
or transfer energy across the ocean.
Yeah.
But it's pretty easy. All you have to do is, like I was not sure if I mentioned that before, but all you have to do is take low frequency waves of high energy density.
Specifically low frequency carrier waves.
That's right.
Yeah.
They carry your energy.
But of high density, and you convert it back and forth from high frequency, low density to low frequency and high density.
Like Tesla came up with the ELF, and everybody turned him down. He offered it to the military, he offered it to the government, he offered it to everybody, and everybody turned it down except for Russia, and I believe Germany, they embraced it.
Yeah, it's incredible. That's what I mentioned when I was in Washington D.C. I mentioned that technology that if we could do that, and I'm sure somebody is working on because you still need a
Well, I think that's what the Tesla coil was designed for. See, I think he created it because there were certain attributes in the Tesla coil that, it's like leaving it in plain sight. Here's the
Mike,
device, and let's
Mike,
figure it out, right? The answers are right in the Tesla coil. Scalar
Mike,
wave.
yeah
the Tesla coil
yeah
was
the
designed to take the high voltage
Right,
and step it down to low
right.
voltage.
Exactly. So there's your free energy
But
right
nobody's using it that way.
there. No, they
They're
want
doing
to
it the
make
other way.
sparks. They want to make sparks.
Right. Well, that's what
what they want
Tesla
to
did
use.
because he knew that would be what they would like. People would
Right.
like to see.
That's how you would
But that's
captivate.
not why he built it, in my opinion. Because if you look at
Exactly.
the secondary,
Yes,
it's got a lot of turns. It's designed for high voltage.
that's
So
right.
it's a high voltage receiving antenna
Correct.
for high voltage signals that are
Yep.
constant.
High voltage, high frequency.
They're not carrying a lot of energy, but they're there. They're constant.
Yeah. So it's
They
high
call that
voltage,
the
high
ether.
frequency, and then you get the second Tesla coil, and guess what you do? You flip it upside
Right, but
down.
you need a lot of turns to capture that high voltage.
Sure.
Because if you don't have all those turns, you're not going to capture it.
Right. It's a
So
step
you
up
need
and
it
a
to be
step
you
down.
need it to be a secondary.
Right.
And so the secondary is really the primary, and the primary is really the step down secondary.
That's right. That's when you receive it. When you
And
receive
you
it,
can gauge your what I think is in reality your secondary. You can
Yep.
gauge that to a very thin gauge because
Yep.
you're not going to be needing to handle a lot of amps here. But
No.
you're going to need to receive as much of that high voltage as you can.
yes, exactly. Yep.
So you need a thinner gauge to create more turns.
Right. That's the key to the Tesla system. High turns, small wire.
And then step that down into your thicker gauge,
That's right. And that's where you get your over
which is
unit.
now called the primary.
Right. So
But it's a
basically,
step down secondary.
that's right. You just flip it
It
upside
should be
down.
anyway.
You flip it upside down. So he gave the answer to our problems a long time ago, and nobody's figured it out. It's a step up, step down transformer.
But yeah, right, either way, it works either way. But
Right, exactly. You just take the second Tesla. Now, here's the other thing too. You got one Tesla coil as the transmitter. Okay, so we don't touch that
here's
anymore.
the thing, though. To get
Hold on, Mike.
signal-
Hold on. You got the one Tesla coil in the middle. Okay, that's your transmitter. Okay, now you take the upside down Tesla coils, and you can put 10 of them all the way around it. Well, guess what? Now you got 10 times the power coming out. Because
that's right. Because you
That's-
can create the one in the center is your
Yep.
high voltage transmitter.
that's right. And all you need is receiver coils planted all the way around it. And this is the textbook of
Right.
the Don Smith device. If you look
And
at
what I was going to say before you stop me is that you need to get a signal across the whole planet. You need that high voltage to cut
Sure.
across everything.
Sure.
It doesn't have to have a lot of amps at all.
right,
It doesn't.
but
It just needs
but-
that high voltage. It'll
Right.
cut across everything with ease
and you know why
without
that is?
disturbing anything, and be received to any ground Tesla coil
And know how that was made
that's on
possible.
the ground for receiving the signal.
Now, there was one
A more clean signal, a more steady, clean signal instead of the ether.
right, but not only that, Mike,
A reproduced etheric signal, more
Right.
localized to the planet,
but don't
and
forget,
more regulated.
there was one more attribute of the Tesla coil that a lot of people didn't know about is the ground wire. He grounded it to the earth, so he was actually transmitting power through the earth. He didn't even need the air anymore. So
No,
if
you
you
don't
make,
need the air either. You could be the air or the earth or the ocean too.
but that's how he made the whole earth resonate to his Tesla coil is by a significantly
I mean,
large
once you get to 30
ground system.
kilovolts, I don't see how anything
Well, he could
is going to
break
stop that.
he could break buildings depending on the frequency, the natural frequency of the building and things like that.
Sure.
And keep in mind, 30 kilovolts at Schumann resonance frequency.
Yeah. But
And
you
how
know,
is anything gonna stop that from traveling? That's that signal.
it's
Low
a
current, though,
harmonic,
low current.
right? It's a harmonic. So as soon as you get that harmonic going in the earth, you match it, and now you increase the amplitude of that signal, and now you can cause earthquakes, whatever, right? But that's not what his
That's
point
not the
was.
purpose of this
That was
conversation, though. But yeah,
no. But that's a different direction you could go. You could also use it as a weapon. Unfortunately, yes. But he
Yeah.
didn't really talk
it
about
would
that.
it would be improper not to disclose that.
Yeah, and I think that was part of the patents that were disclosed in the papers that were taken from his New Yorker hotel. And
You sure you don't need
After he
amps to
passed.
create an earthquake?
well, if you got the harmonic resonance of the earth, now all you have to do is change the amplitude of that wave. And now you can start manipulating the natural waveform of the earth into a harmonic, and you can increase the amplitude or decrease the amplitude. And that's
with your amps.
that's right.
So you need amps to do something like that.
Well, yeah, Tesla coils do put out up to about 2,500 amperes, depending on the scale.
So the Earth's harmonic wave is carrying a lot of amps, obviously.
Oh, sure. Oh, yes.
We're
Especially,
not trying to transmit amps here in this discussion.
no, he's
Everybody that's
basically just
listening, we're transmitting voltage,
he's just
a
connecting
signal, just a
himself.
signal,
Mhm.
a signal wave, like
But
a radio signal.
yeah, he's just matching the frequency of the earth. As soon as he gets into that match, now he's a part of it. Now, if he puts any pressure, meaning by amplitude of the waveform, now he could actually start altering the natural waveform of the earth.
But that's like gigawatts you're talking about, more than
Oh,
that. even.
sure.
Petrawatts.
But he was his grounding system where Wardenclyffe was on Long Island. So he had a massive ground system that actually went into the ocean, and that is probably one of the best grounding systems you could ever use.
I didn't know
the water
Wardenclyffe was
body.
on an island.
Yeah, it was on Long Island, New York.
Oh, that's right, Long Island.
Right. So his grounding system was just as tall as the tower itself.
He actually went into the water with it too, huh?
Yes, he did. Yeah. Oh, yeah.
Then that says it all. There's no mystery here. He's using the water to get
exactly into
it's a capacitor plate. The water,
yeah,
huge capacitor plate. Where's the other end of that capacitor plate?
Yeah, exactly. Well,
somewhere else on the planet ocean, that matches the same body of water.
It's all connected, so it makes it global.
Well, that's the thing. That's if you use low frequency wave, what I wanted to say earlier was the electro-optic modulator that can convert photons of high frequency into multiple photons of lower frequencies, and vice versa. But what I want to say that if you use low frequency wave, you can go through matter more easily. So for example, if you use X-rays, you're not gonna go very far in water with it. But if you use radio waves or things like that, it will go through.
You can penetrate anything.
Yeah,
that's weird because I would have thought the opposite. It would be I would think high frequency would go through a body a lot easier.
Well, it all depends on the surface that you're trying to penetrate. So as soon as you get into harmonic resonance with that object now starts to give way, and the current can flow through that object, right?
So low frequency goes through like dense matter.
Like ELF. That's basically the ELF technology he was working on. He was trying to sell that to the military for the naval, right? Because he knew that would be the best way of doing naval communications. So,
well, that's what the submarines are using to communicate because it goes through water. It's more reliable underwater.
And I wouldn't doubt it for a second of the German U-boats were using that ELF technology for communications.
Did you know ELF works in the air too?
Yeah, pretty much anywhere in any medium. That's why the Tesla coil can transmit electricity through the ground and also through the air.
The elephants use ELF. They
Yeah.
discovered it recently.
I wouldn't doubt it for a second.
One of the trainers or whatever the handlers said they kept feeling the trunk waves of air hit their leg.
Sure. Yep.
And it kept happening, so they eventually.
How about the birds too? How do the birds know how to navigate the planet? They know where true north is. Same thing like a cow. Okay, a cow will only eat food from the trough facing magnetic north. Next time you're at a farm.
That is so weird. You said that so many times. I just can't.
Yeah, just next time you go by a farm, look for cows. And
They'll
look
only
at the
eat
direction.
food from a trough facing north.
Yeah, north. Yeah, I'm dead serious.
The same food facing any other direction, and it's no.
They will always make sure they're facing magnetic north
when they eat.
Yeah.
That is so weird.
That's bizarre, right?
That is weird, yeah.
And that proves that.
I mean, not weird. It's like natural. It's like naturally weird. Like they're connected to the earth in a weird way.
All the animals are. All the animals know if there's an earthquake coming. The birds start acting funny. Dogs start feeling the vibrations. They get all waked out. Like the animals have a direct connection with the planet. They know what's going on. They know when bad weather's coming. They know when a natural disaster's coming. They're early warning.
I think we do too, but we just don't really worry about it.
No, we've lost it. We're not that type of animal anymore. We've evolved into, a techno zombie now.
Yeah, we don't. Fundamental physics 100 years ago was it was great, but since the Nobel Prize started,
that's when all the fake. That's when a lot of the problem is I always found that physicists are electricians' worst nightmare, because back in the day of Einstein and that, electricity to his followers was impossible. Counter space didn't exist.
I can't believe Lulu's got no power.
Yeah,
and we're talking about this stuff. It's like
I know, and she's
got
living
no power.
through. Yeah, she just went through.
A solar light.
She got batteries.
Yeah.
I thought you were doing some Ouija or something.
You got a solar panel?
I don't know how to hook it up. I have a small one, but
that's good to have that and a battery.
Okay, no, I have a generator, but like the two plugs, the one that you're supposed to put in one in the generator and then one into the house. That connection, I don't have it.
Oh.
Yeah, and they have it at the hardware store, and I have to make one. I'm so scared.
You can make one out of an extension cord.
I know. What if I don't do it right?
It's just color code, the same colors.
Same color. Okay.
They're color coded. Right. Just use the same. Wait a minute. You got to plug into the. Right, you need two extension cords, the same extension cords.
Yeah.
Okay.
And just put the. I've done this before. Put the. Just cut the male ends off of the cords and tie them together, and then use that to plug into the.
Yeah.
It's not gonna fire or.
No, just plug black to black, white to white, green to green.
Yeah, just match
wire
up the
nuts.
wires. Yeah, match the wires.
3 wires, the same colors go together. You can't go wrong. Cut the two male ends, the 3 prongs that are sticking out.
The worst thing that will happen, Lulu, is you
2 cords. Two you need 2 of them. Get like 2 5-foot 10-footers or something.
Man, I've got so many. I don't know what to do with them.
Well, they're all the same color, and 2 different cords will work too. They're all going to be either black and white.
Yeah.
And then
if just kind of recap here, people don't know Lulu lives in Texas, and she took the brunt hit of the hurricane that went through her town in the last week. So she's a survivor. The roof was damaged, trees were uprooted. She lost her fence. She hasn't had power in probably 3 or 4 days now. So I'm just amazed that she even came on tonight. Meanwhile, she's like off the grid right now.
Wi-Fi. It worked. No.
The Wi-Fi still works.
No,
yeah,
the car. Car has the Wi-Fi. It's not the house. Yeah.
Yeah, that's great. That's
what category was it?
I don't know.
I thought it was a 4 when it hit. When it hit, it was the 4, and then it loses power, right?
It started to
What-
break up, didn't it?
Yeah,
Well,
and
when we got it, I think it was like 1 or 2, but it had so much
Yeah,
wind.
that's
know,
enough right there.
It didn't have. There wasn't a lot of rain, but it was more of a lot of wind. And luckily, I prefer it like whatever happened versus the flood, because like it wouldn't cost as much to replace a roof or a fence or to clean up the yard from broken branches or a window. But if it's floods, you're talking about like you have to gut half, the first floor of the house pretty much, with the mold and stuff. If like the previous hurricanes, I didn't flood, but a lot of people I know did, and it cost a lot, like really a lot, like it cost anywhere between 50, 60, $70,000 just to take the first feet of the first floor to the rotten wood and stuff like that to replace that.
Yeah, the water damage is the worst.
Yeah, so we were lucky with that one, and so I'm hoping that this is the only hurricane we're gonna get this season. Fingers crossed.
I'm having the same feeling about this year too.
I
the-
honestly anticipate for the season.
Oh yeah, this is actually a very early storm in the season, right? Usually all the hurricanes start hitting around September.
Yeah.
So
Yeah, but when you see storms this early, it's usually that's it.
it's man-made, or something's
If
going
you
on.
don't see any storms early and they come late, that's what you got to worry about.
Yeah.
Did the hurricane go through Florida before hitting Texas?
No.
No.
No, it missed it missed Florida completely.
Okay.
Yeah. I'm just gonna scoot out for a quick smoke here. You guys just carry on with the conversation. I'll be right back.
Yeah.
I'm going to Florida in like 11 days. I'm gonna spend a week there in Fort Lauderdale, beach vacation.
Nice.
Yeah.
I need vacations. I haven't had any vacations for the last 5 years, but I did travel, but it was not real vacations.
No, this one's for the kids before the school starts. I have like some of my I haven't been on a vacation forever, but the kid, like the little ones, haven't been on a plane yet, and so
Okay. You going by plane?
yes, yeah.
So it's pretty hot right now in Florida. Well, why don't you go in California instead?
I don't know. It wasn't my decision. It was the kids.
California is more expensive, isn't it?
Sorry?
California is like really expensive. I heard.
Yeah, I don't know the price now, but it's true. If you live there, it's cheaper because they.
You're in California, Phil?
Yeah, I used to live in San Diego,
Oh, you used to live there?
but that was 14 years ago. But now the prices probably went way
Yeah,
up.
yeah. Recently, it got real expensive. All the
Yeah.
Democrats.
I booked on Spirit Airline. It was let's see, 4 kids, 3 adults. I paid less than $1,000 for the tickets, so it wasn't bad. And then I'm staying at this place called Pompano Beach, like a 2-bedroom suite for like $120 a night for right off the beach. So I think it's pretty reasonable. And then that's also like less than $1,000 for like the whole week, and then just another maybe $1,500-$1,600 for food and activities.
So sorry, how much is a plane ticket?
For 7 people, it was less than $1,000.
For a bunch of people.
Yeah, like 4 kids and me, my daughter, and my older daughter, and her boyfriend. So 7 people.
Oh, that's good. That's pretty good.
Yeah, very good. I know.
Here,
Sounds like you got your hands full.
here in Canada, it's like $500 just to go from Montreal to Toronto. It's pretty crazy.
Yeah, but the deal is this: you can't take any luggage with you because the luggage costs more money than more than the plane ticket to to check in the luggage.
Yeah.
like backpacks. You know, that's all you're allowed. And if we need anything, we'll get it from there. Yeah.
It's
But
been a long time since I flew. What was it, like $5 a pound or more than that, right?
I don't know. Like I think it's
For the
50
luggage.
bag. So I was hoping, like, it's a beach vacation. What do they need? Like bathing suits, t-shirts, and shorts. Pretty
Right.
much. That's it. Like, how much size would that take? Like nothing. Beach towel, and we're done. Shouldn't be more than that. So, I'm like, anything else, we can get it there. So, and plus, my kids are self-sufficient. Like my youngest is 12, so it's not bad.
Okay. Is it a girl or a boy?
I have all girls. No
All
boys.
girls. Okay.
All girls.
So I guess she can cook for herself at 12, or
I have a 12, 13, 14, and a 19.
okay. So they
No,
if you're
they,
away they can cook, I
they,
guess.
they could turn on the microwave.
Yeah, I guess.
You order a pizza.
Yeah.
Order a
Or
pizza.
start a party when she's gone.
Call room
DoorDash.
service.
No. My kids are really they're good
Ring
girls.
up a
Like,
bill.
they'll play with Barbies and Baby
Keep your
Alive.
eyes on that phone.
Yeah, no, they're like they're still they still enjoy Barbie dolls and little toys and slime. And, I don't know, like weird little things. Yeah, but yeah, no, they're still kids, and I want to keep them that way as long as I can.
Yeah. Yeah. So
That's the good spirit. Yeah. It'll break your heart when they grow up, though.
Raising girls,
Just kidding.
really raising girls is tough. So the mentally younger you keep them, the better, because like once they start to realize what the world, then they become hard. But now it's very easy. I could bribe them with the smallest things, and it's good for them. It's all right. But once they get older, it's I have a 19-year-old, and like till yesterday, she dropped out of school like 3 years ago. Yesterday she got her GED exam. She passed. Yay! So I'm really happy. She's back on track. And she literally now is back on the same time originally. So as a gift for her, we're doing this kind of vacation. Honestly, that she's gonna start, I think, college in August.
no, yeah.
Yeah. So yeah.
Yeah. College. Yeah, the big fun years.
We'll be good. He'll be all right. Well, we will live. We'll survive. Yeah.
In what field in college?
I don't know. I just need her to finish apply. I think I want to send her like to community colleges for the first 2 years while she did, one, give her time to decide what she wants. Two, it costs, way less. And
Yeah.
so
Yeah.
you guys don't, right? I never asked. I know Mike has like children, but I don't know if you and Mike do.
No, me, I don't have kids because I wanna work on my business first. So I knew it was going to be hard, and it is indeed hard, harder than I thought. But as soon as money flows in, then I'll be more open to have kids. So it doesn't matter the age for guys. That's fortunate. I can wait. I'm 47 right now. So
Still
it
young.
doesn't matter.
You never know, Phil.
I'm the old
Someone
fart
might
here.
surprise you.
I'm the old
don't-
fart.
It is 20. You're like 67. You're like, just think of it like that. Like, you want to enjoy it while you're young, not while you're old. So
Just have a young wife. That's what you need.
Yeah, exactly. Yeah.
Definitely makes it difficult at times when you're trying to concentrate on your career, right?
Yeah.
I don't know. I decided to go the other way, or hand in hand. Let's put it hand in hand. Like, have the family and slowly work on the business part, and a little bit of like both. So I feel like I did the right decision in that respect. I didn't want to be too old while I had children. I mean, I see moms that are 20 years older than I, and they're like they have like itty bitty kids. It's like, how do you even have the energy to take care of these kids now?
Yeah. I'm a with me, I'm a little bit older. My daughter's 12 now, so she's more doing her own thing now, and she has her own thing, and it gives me a little bit more free time. You don't have to attend to a baby, right? It's different.
Yeah,
Question: Can your 12-year-old cook?
Yes.
Oh, she can't. Oh, wow.
Yeah, we're
Yeah,
teaching her little by little.
I like my kid can turn the microwave.
yeah. I would love to have kids actually, but I just not in the early stage when they cry during the night and things like that. So, that's not
That's
really.
half the fun, man. Yeah, it's half the fun,
2 hours.
especially. Yeah.
Nightmare.
Yeah. And when they get older, you get a little bit more of your freedom back too, right? It's the first like 3 to 4 years that are kind of tough,
Yeah.
and then as soon as you get past that, then you don't have to change diapers every half hour, right?
Yeah. Exactly.
Phil, you have a lot to look forward to, especially like the terrible 2s and the terrible 3s, where everything is no. Like there's no logic. It's just no, and you try anything else, tantrums. Like, yeah, you've got a lot ahead of you. There's no behind it. You cannot logic. You cannot reason with them. You just have to go with the flow. You don't want.
Exactly.
Mike's got a video here he wants to show. What are we looking at, Mike?
This is something Stephen Drysdale sent me earlier from Action Forbes.
Oh, okay.
Something to do with field reflection of the flyback. The flyback being a reflection of the circuit reflecting off the impulse, something like that. I'll just play it. You ready?
If I start a wave at this end of the machine, that wave travels down to the far end, is reflected there, and returns as a reflected replica of its original self. But now let me terminate this machine in a different way. I'll clamp this last cross arm to a heavy stand so that a wave arriving here can't produce any displacement of the cross arm. This time you see the wave is reflected upside down.
Oh,
the reflection is still total as it was before, but the wave is inverted upon reflection. Nice. In a mechanical wave system, then, there are 2 ways in which the total reflection of waves
By the way, I
place.
didn't watch this yet.
So it's a reflection,
right side up,
is the
if the reflecting end of the medium is completely free, and upside down
The
if the reflecting end is completely restrained.
Like the reverse flyback.
Now, if nature has any consistency, and we like to think she does, this alternative reflection possibility should exist for waves of all kinds, and these other drawings here show that indeed it does. Take the case of an electrical transmission line, for example. You know that there are 2 ways in which electrical waves can be reflected, depending on whether the far end of the transmission line is terminated by a short circuit or by an open circuit. And similarly, in the case of waves traveling down an acoustic tube, there are 2 different reflection possibilities, depending on whether the end of the tube is closed by a rigid termination or by the acoustic analog of a free end. Note that in the mechanical situation, a clamp is a constraint preventing the displacement of the end of the wave medium. The electrical analog of this state of affairs is an open circuit termination on the end of a transmission line, preventing the flow of current at such a termination. Right. And the acoustic analog is a rigid closure at the end of an acoustic tube, preventing the longitudinal vibration of the air. Right. In all of these cases, the reflected waves come back upside down. And in all of these other cases, conversely, which are analogous to the case of the free end of a reflecting wave medium, the reflected waves come back right side up.
That's interesting.
So what does that mean? Like, can you guys explain it?
Okay. When you go back, I'm gonna go back a little bit here where he points at the right here, that tube.
Okay.
The top tube, you see the right side, the ends are open.
Yes.
So the wave can vibrate outwards into the air.
Yeah.
Okay, and the bottom tube, the ends are closed. Okay, assuming to the left of that top, the middle tube there, to the left, the one he's pointing at now, the left side of that tube, you see the round thing with the signal.
Yes.
That I believe that means AC input. Like you're connecting a signal to two ends there. Yeah. So the other end of the two rods are open, so this your signal vibrates on those two rods outwards omnidirectionally or out the tips even. So now if you put the signal at the bottom tube on the left side where the signal goes in there, again, the left side of that tube, then if you close the other end of that metal tube,
right, it will return to the source, but inverted.
Right, but he also said in both circumstances, the reflection of the signal is inverted also.
Yeah.
Even though one signal's going outwards, which I find interesting.
Right.
So, and the other one's going inwards.
Right. So this
you would think that's not supposed to happen that way.
Right. So that's how you get the inverted wave on the back EMF flyback on a pulse motor.
You know what that says? That says no matter the geometry, that
it will always
the return
invert
reflection is coming from a universal geometry.
Right.
Meaning there's some kind of geometry that does not depend on any specific one geometry to reflect in the inverse every single time, no matter what's your geometry on your transmitter.
Right. It will always be inverse.
It will always be the inverse.
Right.
So
that's the point of this video, I think.
Would it cancel out the original signal when it goes?
No, it will be the inverse. It will be an inverse.
Anytime
your signal.
Yep. Yep. So any signal you send out where the waveform's above the line, when it comes back, what we call flyback or return signal, it will always be the direct inverse.
Polarity.
Right.
Not the same shape as your signal going in.
Right.
Of course, a different shape coming out, but the polarity will be inverse every single time.
Right. So
okay, going back to this video, the polarity. Let me go back. Hold on. Look at the wave at the top. That's positive at the top, and how it comes back negative.
Right. So
this self.
See what?
But now let me terminate this. That wave travels down to the far end. I'll clamp this last cross arm, is reflected there and returns
comes back at the bottom
as a reflected replica of its original self. But now let me terminate this machine in a different way. I'll clamp this last cross arm to a heavy stand so that a wave arriving here can't produce any displacement of the cross arm.
Yeah, a
this
reflection.
time you see the wave is reflected upside down.
Yeah.
Because there's. Okay, I got it. I now understand.
So he created a wall by clamping it. He created a barrier, like you can't go past here. You're Mr. Signal, sound wave, whoever you are, you're going to hit this clamp that's not allowing any vibration that go any further, and you're going to have to find something to do. And what do? Instead of what you did the first time, going back on the positive ramp backwards the other way on the positive side, you go on the negative ramp backwards.
Right. That's right. And this is your classic Hertzian wave, especially like in an AC transformer. If you look at the waveform, it's a wave above, below, above, below. That's when you get that reflection coming back.
So how do you bypass this where you want to put out positive but get positive?
You don't create a wall. You don't create a barrier.
You leave it as an open circuit.
Open circuit. All right. Okay.
But wait a minute. But then he shows later the top tube as an open circuit, and he says it still comes back inverted.
Right. Because he's talked about Well, because now he's saying by the natural frequency of, nature, it always will go back, on the inverse. It's just the way nature works, right?
Because my train of thought is going like in space when we send out a signal, and if we get the signal back but in inverse, it means we hit a block or
Just a limit of where
It's
that
like not
frequency
creating
can
a
travel.
block wall or a wall to stop the signal, allowing the signal to vibrate, continue to vibrate back on itself is what's going on currently in nature. But as soon as you try to put a barrier up against nature, you become the absorbing factor of that energy. You take in the momentum of the force that you're stopping.
Now
How do
that inverse coming back, would that be a representation of what cold electricity is? Which I think it probably has some kind of relationship there.
That's just weird how it reverted. It reverted. When the wall was established with the clamp
Hmm.
to stop the vibration, it still wanted to keep going.
Yeah,
So it went under in the negative side because it had that opportunity.
it had that pathway to go.
Somehow it found the way. It created. It took the wall that you created, the solid, non-vibratorial clamp on that bar, so you can't vibrate no more.
Right.
And instead, it
It
found a way to
transferred the
bounce
power
off the
down.
wall.
It transferred the
vibrate.
power down.
It
or
didn't
the
vibrate
signal.
off the wall. It bounced off of it.
It bounced off that top wall and hit the bottom wall, and instead of going up in the wave,
Right.
it went below in the wave. That's
Instead
why
of vibrating that last bar that was clamped down, the bar refused to vibrate, and it reflected the signal back onto the last bar that tried to get it to vibrate.
Yep.
Did that make sense?
Yep.
Yeah.
The last bar in the sequence was the one sending the signal to the last bar that was clamped down, not allowing any vibration. That bar did not allow itself to be vibrated. Instead, it did allow that vibration that came in to reflect off of it onto the bar that tried to vibrate it in the first place. But by the time it reflected back, that bar that was sending the signal stopped vibrating and was now able to receive the same vibration it already threw at the wall.
Do you think the end would matter if it's at a different angle instead of it being like capped like this? Let's say if it was like that, wouldn't then like this and then bounce back up instead of it if it's like this bouncing and then it's going back down? Just where
if the last bar was still vibrating when the signal was coming back at it, its own signal, then it's possible it couldn't go in the positive path and it had to go the negative.
Right.
Which is why it curved down.
It
had some of its own resistance saying go another way.
Well, it's like a deflection. That's all really what it is deflection.
I mean, it's 3D, vibrations are not two-dimensional.
No, they're three-dimensional.
So they have many paths to choose.
One of your better videos.
Even in a two-dimensional bar, right? Because they could still find a three-dimensional path through that bar.
This is definitely one of your better videos for sure. Yeah. Really cool demonstration.
I like when I see the experiment rather than it just being,
Well, the experiment is everything. And then when you get the experiment and it works, then you try to figure out how it works. Everybody tries to do it on paper first. Try to make it, use your own intuition and come up with your own ideas and make the experiment. And if you're successful, then after that, that's when you start back engineering something.
Seems like the last bar unclamped was able to take the full vibration
and transfer it to the other line. It was a deflection off the main.
Yeah. Very interesting.
But that will give you a better insight on how Hertzian waves work.
Man, it makes me think a billion things at this by seeing this. Like
These old 50s demonstrations
like
are crazy.
Oh yeah, they were. That's why it's hard to find them now, because these were like cutting edge. Like this video is like a physicist's worst nightmare. They do not like this stuff. No.
Why? Because it raises too many questions outside their mathematical equations already.
Exactly. Yes. It
They
challenges
can't
everything.
put the math to it.
That's right.
Yeah, that's another thing. It's pretty easy to people claim that these days they all brag that I got a PhD, blah blah blah, but it's pretty easy to
You can't even put simple math to this, Phil.
Yeah, it's
Even
pretty,
the simple
it's pretty,
math, the multiplication, divisions, you can't even put that to this example you saw here.
Yeah, I know it, because it's not written in textbooks, so it's a lot more complicated to write something from scratch than repeating what's already in textbooks.
Yeah, like a perfect example of it would be Professor Lathway. He did all those magnetic experiments. He got ousted from the university he worked for because he was doing stuff that went way too far for their liking, and he was ostracized by the universities he was working for. And yeah, so
Yeah, that's
you know,
ridiculous.
You guys are
But that's
familiar
not
with the
science,
metric system, right?
yeah,
Yeah,
You
that's
know how
not
you go
science.
behind the zero and in front of the zero? Behind the zero is negative,
yeah, into the
in
net.
front of
Yeah,
it's positive. So that's what I think is the closest thing to these polarities
right. He's
going on
showing
as
you
far as math goes.
he's showing
It's-
you an analog version of the math.
it reminds me of when like a lens, when you put you put a signal out for, like this way, and then it lenses it negative, but this one is on a different kind of thing, but it's like a lens.
Yeah,
How
but
it's
that would be more of a point source thing. So I
mm,
think your characteristics would change if it's a point source, because like a sun going through, say, like um, a magnifying glass, and then you're able to burn something on the ground, right? Like a leaf or whatever. That's a point source technology. Actually, Ken Wheeler talks about that quite a bit,
okay.
and he says, for the longest time he didn't believe in free energy, but when he figured out that the only way to get like real powerful free energy is by point source, so that's up for debate too. But I think you can do it in many forms. It's just a way you got to work around the laws, right?
Yeah,
If you can defeat Lenz's law, that's a huge step right there. Not like Lenz's law is Lenz's law; it's there, but you can do it by the engineering, and that's where the physicists and the engineers have a huge problem. It's because in the math they say, "Oh, Lenz's law cannot be beat." Well, then the engineer will go, "No, I've been able to engineer, a system where the Lenz law has no effect." So that's why physicists are, an engineer's worst nightmare, especially an electrical engineer. They don't like it because they can circumvent some of those laws.
So
The first law of thermodynamics, energy cannot be created or destroyed. But I think the second law has got some issues, and I think those issues are why people are able to come up
what's the
with
second one?
um, um, let me get it
I
offhand. You
got
put
you.
me on the spot again. Second law. Let's see. Second, I want to get the proper definition so I don't
Going back
bastardize
to
it.
the lens thing, man. I don't think anybody's tried this, but how about a
Second,
bifilar stator coil for picking up magnetic fields? Nobody's ever created a bifilar stator coil.
okay. Second law of thermodynamics. They state that when you put energy in, you can never get the same energy back. You'll always have less
That's the
energy
second
coming back.
one.
Yeah.
except with superconductors.
What
Now,
about
Except for
Yeah.
superconductors, right? Which
Right.
are have zero
Or
resistance.
or
technically speaking.
what we've been working on, the back EMF,
That's
you're
correct.
able to put in a small amount of power and get more power back, which is in direct violation of the second law of thermodynamics.
Do
Now,
you suppose that a superconductor, because it has no resistance, will create no magnetic field when the current's flowing through it?
well, automatically the
I mean,
second
don't you need the resistance to make that magnetic field?
it's at, well, yeah, that's
You
where
know,
that's
you just need the charge in motion.
right. It's charge in motion, but see it by
Oh wait, you
reg,
don't need. So you don't need the resistance. You just need the electron flow,
the,
Yeah.
just
which
the
makes sense
sec,
also. But
right.
you're saying the resistance has nothing to do with it?
Yeah, like the second you put energy through a wire, a
The
magnetic
reluctance.
field is created. Okay,
Right, right. That's from the electron flow. The flow of
right,
electron. Right.
right.
That
See,
creates a magnetic field.
see,
But
you
But
know,
you still have resistance in the wire. Now, if you were using a
right.
superconductor, would that magnetic field still be there?
Well, we've never created one, so we don't know.
Well, I would say yes. You would
Yeah,
have.
I would say yes too, because you have electron flow.
Yeah.
Right. Yeah.
But how
I
strong would the field be? Would it be the same strength,
right. See,
weaker, or stronger?
right. Because see, like especially in the lens
Maybe
effect.
stronger because you got no resistance and
See,
you got 100% flow
right.
of the electron.
Like say in your typical motor, Lenz's law takes effect because it's the cogging of the magnetic field, right? So we know when you cut
But
the
that
power off,
seems to cause the field to
cog itself. Yeah,
saturate. No.
yeah. Well, it cogs itself. It causes resistance, right? That's the main reason why you get lens effect, right? So if it like my switching technology that I use in my Adams motor, the second you release the physical connection between your inductor and the power source, now you have zero resistance because there's no more current flow going through it. So if there's no current flow, the magnetic field in the inductor now collapses and disappears.
So you
So,
lost me. If you have a low, you have, because you have no resistance, you have no load. You're saying,
well, it doesn't detect a load.
oh, right? It doesn't detect the load, but it
Right.
detects a short.
A short, yes, because there is still physical power going to that inductor, right?
So you're saying that a source power will not
When you
provide
time it,
any of its source to a short?
well, say that again.
You're saying a source power will not provide its source to a short?
It will, yes, if it's a
It
closed
won't be
loop.
heat though, because
If
there's no
it's if
resistance.
no, but if it's a closed loop, it will, yes. But
Not without
like,
not without
but
resistance. Where how are you going to build
right,
heat?
okay, like I was saying before, how my circuit works is the physical connection of that circuit has been broken.
It's
Okay,
open,
it's a now open circuit. What do we know
right?
about open circuits? That's how you can get free energy. So that's why I use the switching technology I
No, I
use.
mean
The
I'm talking about
second,
the superconductor short.
it's all related to the same thing. The second you release the physical power source to the low or to your circuit, now the current flow now ceases to happen. Now you're working with the reactance that's left in the coil. Now you're getting a coil field collapse at the same time. This is all happening within a nanosecond of it being switched off. That's why I'm able to defeat Lenz's law is by making that physical break. All right.
Fast
Now,
enough.
now the
Fast
resistance is
enough.
on.
A quick break.
Yeah, it has to be timed perfectly. If it's not, you will get the lens effect.
What would
If
you
you got
recommend for a really good, the fastest switching device that you could possibly find?
well, see, the only make and break that I have that's readily
It
available.
doesn't have to be a physical contact. It could be a gas tube or something.
No, it has to be a complete break in the circuit. There cannot be like say like a
You can't
MOSFET.
use gas tube to create a.
I don't know. I don't know how I would engineer that to work.
Don't they?
But that's why I'm
gas
using
tubes?
Excuse me.
Isn't that like the same thing as a spark gap, a gas tube?
Basically, yes. That's exact. And what did Tesla work with constantly?
So
Spark
when
gap.
the gap closes, you have a switch closed.
Right, exactly. What do you think Tesla worked with it? Mind you, at that time he didn't have MOSFETs, he didn't have transistors.
So he
didn't have,
used spark gaps to get it
yes,
the
right.
quickest switches he could create.
That's right. And that's where the second you make that break, the resistance goes to zero.
Right, because if you had it held down too long, you'd be harder
You're
to
drawing
break free.
current. You're drawing current.
Right, the current's holding your circuit closed more.
That's right.
And,
it's a
and to
closed
disconnect,
circuit.
it's like trying to lift the switch after it's been, connected so long.
Stefan said a accurate thing. It's a break pulse, right?
It's like you were saying with the big
Yeah, with the old
switches.
the old switches, the old what do you call it, knife switch.
Right, if you close it, you can open it right away with no resistance. But if you close it and it stays closed and that current's flowing for a while,
Because
then you try
it's
to
now
open it, you
right.
can feel that you got to pull harder.
That's right, and it becomes a closed circuit the second you make that connection. The second you release it, now you got an open circuit. What does Tom Bearden talk about? Keep your circuit open. Let the current flow. So now with all that energy that you have stored in your inductor or your coil, now you got the reactance working for you. And
As long as you have the diodes channel, will give it a place to go. It will go. Yeah.
But don't forget, Tesla didn't have the diodes back in those days.
What did he have?
He had nothing. He had to work around that. I'm not sure exactly how he
build something.
No, he didn't have it. We're talking the 1890s here. They didn't have
graphite. Wasn't that available?
He could have been experimenting with something like that, sure. But as far as I know, he didn't have it. He didn't have any kind of diode.
So he was stuck.
He was stuck because the technology hadn't been invented yet.
So he couldn't redirect anything.
Could have you used crystals to gather that energy in?
Well, he could really control the amplitude of the reactance happening in his coils. So the second you open that switch up, man, you're going to get a hammer of power. Like no tomorrow.
Yeah, he can create the radiation,
Yeah, because
he couldn't redirect it because the semiconductors do that.
See, back in those days,
diode.
So when he started developing the Tesla coil, he also developed the rotary spark gap. And that was
stuck on the coil. If he could put a diode on that coil, he could get it off the coil as soon as it's created.
But Mike, we're talking 1890s.
Right.
He didn't have that, right?
Right. So what did he do? He just went ahead and used it right away. Threw it into lights and
whatever, into a condenser or whatever, or through the ground or whatever. But at that time, his quick switching device was a rotary spark gap, which he pretty much invented. Right, that was the only way he could control the frequency of the actual pulse.
Yeah, because he had batteries back then, didn't they?
Yeah, they had batteries. It was no problem. But now he's got a motor. He can control the RPM, and the RPM.
A battery is kind of a diode.
Well, yeah, but I don't think. I don't know what he was working on at that point, but I don't see any kind of literature pertaining to how he.
But the high voltage he was creating could not go into the battery without destroying it. Even the batteries in his time.
Well, that begs the other question too. What was he doing with that back spike? How was he controlling that?
Did he have it? Do you know of him having any batteries in his lab, or?
Well, he was using the mains. A lot of it.
He never had batteries.
He didn't, as far as I know, he didn't work with batteries. He worked with AC current coming from the wall or from the mains. So now the only way he could do it is say, if he had a battery run an AC generator, and then that way there's
capacitors
no
or
physical,
whatever, but not battery, not
he worked with a lot of capacitors. Like they were all very, very large scale capacitors or condensers. He calls them condensers, not capacitors.
So he was trying to get some kind of storage going on.
Oh, for sure. Oh, his Wardenclyffe Tower, the one in Colorado Springs. I've seen some of the old pictures of it, and he had these massive banks of capacitors. Massive. like enough to fill up.
Capacitor.
Huge, standing 2.5 feet off the ground. Like we're talking like square meters of capacitance.
Oh yeah, something like that. You don't need batteries; they're obsolete now.
Yeah.
That's
yeah,
awesome. You kidding
but-
me? Where did he have the resources to get that built?
well, he had his investors, right? He had the investors back then. And
Were they oil-filled capacitors or?
Yes, some of them were. I'm not sure if they were using ceramic back in those days, but I know, yeah, there were a few. But a lot of the stuff he actually had to build. You know, a lot of the components he actually had to machine himself.
Yeah, you can build capacitors too today.
I've built high voltage capacitors myself, and it's actually a lot easier than you might think, because like capacitors don't store energy; they store electrostatic charge, right?
No, they store energy. I mean, the circuit will run after you.
No, they store electrostatic potential. They do not store electricity in it. It's electrostatic. When it breaks through the barrier and goes to the second plate, and if you start drawing off it, that electrostatic charge that's inside the capacitor now becomes electricity again.
Right. Yeah, it stores pressure.
Yeah, it stores.
It's like you're pressurizing it.
It stores electrostatic pressure, because that's why if you discharge a 15 kVA capacitor on your fingers like I did, it doesn't feel very good. And I've done it, and it felt like I had a heart attack after I did it. It is not fun, and it hits you hard too. Like I'm talking
from
like
the microwave.
No, I had the little ceramic 15 kVA capacitors, and I forgot to discharge it once. This was going back a few years ago, and I shorted it. I grabbed it like this with both, went right through my chest. I thought somebody took a sledgehammer right to my chest. Almost knocked me off the chair. Like that could have been actually dangerous what I did.
What was the microfarad on it? Do you remember?
Oh, it was that one there, I think, was 20,000 microfarad. It was pretty high, but 15 kilovolts. Oh, it hurt. Let me tell you, that was the worst.
25 microfarad, you said?
2,500 microfarad.
That's a lot, dude.
Yeah, it hit me hard, man.
At that voltage? You're alive?
I don't know. Yeah, exactly.
I got hit by 480. And
it felt like Mike Tyson punched me right in the chest.
Yeah, I know. Yes, that's right. It feels like a bull just ran into you.
That I learned a very good lesson that day, and thank God I was still alive for it.
Took me 6 months to recover from 480. How long did you take to recover?
Oh, I was shaking for a good hour.
No, I mean, you weren't sore for like months after that?
No, because it was a really quick discharge on me. It was like
you didn't get a full grip on it or something.
No, thank God it was just my fingertips that had it, right?
See, I got hit by the back of the finger, and I was sweating a little bit when it happened. So
you were more conductive.
Yeah.
I got electrocuted when I was a kid, but it was a 240 volt. Overseas, not the 120 here, and it threw me 10 feet.
Oh yeah, it makes your muscles just freak. Your muscles just tense right up, right?
I've never been shocked like that, but I've been shocked over 100 times.
Yeah, because because it was such a small microfarad capacitor, that's probably why I'm okay. But if it was any higher than that, I wouldn't be here right now. That would have stopped.
Smoke coming out of me, smoke.
You must have really grabbed the line,
Oh my! Well, you tense up, you can't let go, right?
It was a metal gate. I don't know. I guess the metal gate, something was shorted, and so I was climbing on this metal gate, and then it gripped me, and I couldn't let go.
Because you tense up. Yeah, you tense up.
And then all of a sudden, it just went poof, and I flew back like maybe 10 feet. Yeah.
You're lucky to be alive from that.
Was this in America?
No, it was overseas. like it was 240
Third world
volt.
country.
Well, my cousin got shocked really bad.
They don't do good electric in the third world. You got to be careful.
Yeah, my cousin's an industrial electrician. He was working at Pearson International Airport when they were
Unless you're in
building
the city.
when they were building Terminal 2, and my cousin worked there. And usually, when you work on a circuit in a building, they have a box where the breaker switch is, and you lock it out. You lock it, right?
Mhm.
So my cousin's working on this main. It's putting out, I believe, 500 or 600 volts at like 200 amps, and somebody cut the lock off and flipped the switch on my cousin. That blew him back 20 feet. It burned all his fingernails off. All his fingernails were burnt right off. He was in the hospital for about a week with a heart monitoring his heart.
Oh wow.
And yeah, he could have died. He could have died from that. It blew him about 20 feet away from the box.
Well,
So yeah, severely dangerous. Yeah.
Not everybody's so lucky.
No,
I don't
no,
know
that
how
could have
I
killed
got
him.
so lucky. I mean, I told you, I've been zapped over 100 times. I've never had a
like his
bad,
hands were,
instant.
like his arms were burnt all the way up to his elbows. Like we're talking like severe burns.
Yeah, I know. I've seen electricians,
Yeah.
almost lose their face.
But my first question was, who cut the lock off? And it was yeah.
Very
That's, that lock's on there for a reason, to keep the switch closed while he's working on the circuit. Somebody cut it off.
You know those big screwdrivers, the big flatheads?
Yeah.
I was working on a meter once.
Yeah.
And I accidentally touched the side of the
Ooh.
to the panels
Yeah.
casing. The thing melted right in my hand. Big flash, like the fireworks went off.
Oh yeah, fireball. Yeah.
I was partially blinded for like a minute.
Yeah, you got
not a scratch. Didn't feel a thing.
You got the welder's flash. No, it's dangerous.
I'm blessed.
Like thank God I'm working at a small scale, but even then, even I'm working at a small.
You can throw
scale.
me in the middle of a power plant and nothing will happen to me. I'm telling you. I could rub the back of my hands. Okay, I'll stay away from there. Oh, be careful there.
Well, the one hand rule, right? That's when they came up with the one hand rule.
I go like this. Oh no, there's power there.
Or if you're going to touch something that's potentially alive, I was told, touch it by the back of your hand.
Because I have the meter to check for. I don't use it. I use my finger.
No, but I'm like, if you're out in a situation and you don't know if it's alive, you don't want to touch it this way.
Like that.
You touch it with the back of your hand, because if you tense up, if the line's behind you, you tense up, your hand's not going to grab the line, right?
But if you're confident, you can just go like.
No, you're really going to take that. You're going to take
the wire and I go. Yeah, power.
Okay, everybody, don't listen to Mike.
but you're Mike. Both of you are Mike's.
Well, sometimes you have to.
I told you, I've been shocked over 100 times. Unless you want to get shocked over 100 times, you listen to me then.
Okay, so now we know what happened to you.
Yeah, but no, I never got no serious bites. I mean,
it only takes. Bites, it only takes that one time, man, and then
yeah, I believe it. I've seen the instances. I just don't know how I got out of it all these years. I still do it. I'll still jump into a panel. If somebody knocks on my door, say, "Hey, come fix my panel." No problem.
Well, just make sure you shut the circuit off before you start working on it.
Well, first I leave it live to figure out what the problem is, and then when I figure the problem is, then I turn it off and then I fix it.
Well, we're in the modern age now. We do have voltmeters, so you can test every single part of that.
Yeah, you could turn it off and still figure the problem out.
Sure, of course. You got the instruments to use it, right?
A lot of the times, it's not even the wires or the panel. It's just the breaker. Change the breaker. They act fishy.
The faulty breaker switches. Yeah.
They'll work halfway. They'll give you like 90 volts, and your light will look a little weird.
Yeah, and that's when you got to switch that breaker circuit out.
I have a theoretical question for you, just to change the subject. To go back on the 100 years ago comparison with today. They didn't have the internet and things like that back then. So the media, it was harder to get in touch with somebody remotely. But I mean, there's these days we can, but there's so much disinformation.
Yeah.
It's harder to sort out the truth, the legit things from legit things
Yeah.
from
Yeah.
the
Folklore and legends and yeah.
disinformation and things like
Yeah.
that.
Hmm.
So, what's your opinion on that? Is it
That's
Well,
where experiment comes in. They
yeah,
don't lie. The experiment doesn't lie.
start off small like I did. I'm not electrical background, not electrical engineer. So I started off small, making simple circuits and learning along the way. And yeah, from time to time, I've had a capacitor explode in my hand. That doesn't feel good, not alone, scare the hell out of me at the same time. So you're going to learn along the way, do a lot of reading, look online. There's a lot of resources online where you can learn how to build simple circuits and just start off small and work your way up.
Yeah, but I mean, because yeah, I'm doing a lot of self learning and things like that. But I was just more wondering about the if you want to spread the word and get known and things like that, get
Yeah,
your
yeah.
work known,
You
get
have to,
marketing.
you have to talk about or you know, uh, search on the guys that started with all this stuff. Faraday's a good place to start. Then Tesla, Steinmetz, Heaviside, J.J. Thomson, Maxwell. Start studying the Godfathers, the guys who started the research, right? That'll give you a really good background on where all this stuff derived from, right?
Yeah,
So that's where you want to go. You want to see what Tesla was working on, but like people have to understand, yeah, Tesla pretty much created the modern world that we have now. This, the AC power systems that we have now, it's 120 years old. This is old technology and we're still using it today. Tesla already knew the direction that we should have went in, but the powers to be, the power brokers and all those guys wouldn't embrace it because they didn't like the fact that they did not have control. That's the
yeah.
big thing, is the control.
Direct current or alternating current for like in general,
Well,
as in electrical.
well, when Edison wasn't wrong either. Batteries have their place in our society. We use them all the time, our cell phones, computers, all that stuff. But for long distance transmission of power will always be AC,
Okay.
where DC could only go a couple kilometers and then the power drops right off dramatically.
No, in a couple kilometers,
Yeah,
couple
but
couple hundred feet.
AAC loses power over distance.
You needed
Well,
a
Over
really
no,
thick
distance.
it'll
wire to
travel
transfer.
way further distance, and the wires can be very small too. Where DC, to get that same distance, they have to be like 2.5 inches in diameter to get that distance. Where AC, you could have small wires that are the size of a quarter, and
And the AC carries the same amps as on a smaller wire.
that's right, right. So that's why for
Tesla
long
knew that way ahead of time.
Oh,
He wasn't
he
worried
was
about
he
it.
was he was already way beyond that. He was already working with the wireless technology at that point. To get his legacy will always be known as the transmission of electrical utilities for the masses. That will
Hey
always be.
Phil,
Yeah,
uh, you're powering your MHD with plus and minus, right?
yeah.
You ever consider flipping the polarity back and forth on that plus and minus to see what happens?
Yeah, I did so, and then had the same effect. I thought that the weight would there would be a weight gain in one
No,
direction.
did you flip the polarity fast or like
Oh
quickly?
no, you mean alternating the polarity?
Yeah,
No,
like a high frequency polarity flip.
no, I didn't do that.
Look,
Are you talking
get
about?
yourself a double pole, double throw relay, and let me know when you got that in your hand. They're like $10-15.
Now, what are you gonna run with that? A AC motor or a DC motor?
No, the MHD he's got. He's powering it with plus and minus. I'm saying he should try, flipping the polarity on back and forth to see what happens, just as an experiment. I don't see it damaging anything,
No, it's not going to damage. I'm curious as well, so to know.
You could try doing that at different frequencies, flipping the polarity. You might create like a large amount of eddy currents that way.
Yeah, that might create some heat.
Back and forth like that, eddy currents.
Yeah, that might create heat. That might create some heat, and then you'll get a lot of resistance. You'll have to worry about the windings.
Well, heat, he could always slow down the frequency if it creates heat.
Yeah, well, it's resistance, hysteresis. You're killing the power in it.
You mean from the reversing of the polarity?
Yeah.
I mean, what's the metal hysteresis from the gallium?
Oh yeah, talking about gallium, did you know that there's a gallium anomaly? It's pretty cool. It's on my WhatsApp group, but I'll share it with you right now.
I think that hysteresis vanishes when you hit key frequencies, Mike. To be honest, it
probably does.
It really does because you're good. You're getting in tune with the eddy currents to be at the right rate that they like to flow at. That way, the hysteresis.
Yeah, if you match if you can match the frequency,
they're just spirals trying to work with each other in opposite directions. You got to figure out what speed or rate of oscillation that is to prevent hysteresis.
Yeah. Well, you'll know if your circuit starts to heat up.
Yeah, I don't worry too much about hysteresis. That's just all those things that they pump into the traditional sciences that are valid arguments to consider in all experiments, no doubt. But I don't think you should let it interfere with your ideas and where you're trying to go with stuff.
This is actually a good segue.
It's just an experiment. It's an experiment,
Right. This is actually a good segue. I'm glad you brought it up, Mike, because Steinmetz back in the day was working for Henry Ford, and he had this motor system or generator that he was working on, and it was always overheating. So
that's the hysteresis, right?
Right. So he called up to Steinmetz and said, "Look, I got this problem with this generator. It keeps overheating, and I can't figure out why." He's got his engineers working on it, and they can't figure the hell what's going on with it, right? So
fuel generator or electric generator?
I'm not. It was an old electric AC generator. Henry Ford was using it in one of his very first factories he was building for the Model T.
Were there permanent magnets in it?
Yeah, there was permanent magnets in it and giant windings. The motor stood about 10 feet off the ground. It was a large generator.
Yeah, the magnets will create the hysteresis with the coils.
Right. So what he did was he came down with basically a ladder and a piece of chalk, and he went and did some calculations on the actual core of the generator,
the iron core,
and determined in this spot for some reason the generator core is too dense. He said you have to take
too much iron there or whatever.
Right. So what he did, he figured out mathematically how to reduce the density of the core in that section of the generator. Told the guys by basically a piece of chalk, and he drew it out on the actual core itself, and told the guys, you got to remove this segment,
chop it off, cut it off, or whatever.
Cut it out.
Okay. How did he determine the density?
His mathematics figured it out. So anyways, this is actually a true story. So anyways, Henry Ford calls him up and he says, well, how much do I charge you for the repair it? And he goes, it's $5 for the ladder and 25 cents for the piece of chalk.
Oh, God. Henry Ford.
He goes, yeah, Henry Ford, he was doing the work for. And Henry kind of laughed and he goes, no, seriously, how much do you want? He goes, well, But yeah, $5 for the ladder and $10,000 for the chalk.
So wait a minute. If he was using math, if he was using math, he must have measured the coil wrapped around the iron.
He
And
did.
I know how to do that, by the way.
Right.
One of
and
my teachers told me
Yeah.
a story how he
that's what he did.
He
That's
worked
what he
at
did.
an airport, Mr. Lundberg at ITT.
Yeah.
So he worked at an airport, and one day at night, the airstrip lights just went out.
Yeah.
One of the motherboards, it was a series connected of motherboards for each light
Right.
along the airstrip, and they're in series. So if one of those boards fries, the whole thing goes.
Yeah.
So they switched it later to parallel, so you don't have that problem.
See, usually what happens, like the transformers you see on the pole outside that steps down the, 20,000 or 30,000 volts down to, 120, right? That transformer, if over time you get heat, like those drums, they're filled with oil, right? To keep them cool. What will happen eventually, because they heat up because the harmonic that's being created at the substation goes out of whack and creates this weird harmonic. And what will happen? It'll actually breach the core
Same
of the
thing
transformer.
like the iron core.
That's right. And
Except
that's why
the circuit is finding another place to extend it.
Right. So eventually the windings, they get breached and create this heat spot inside the transformer. And then sooner or later, that heat builds up. It builds up because the harmonic keeps going on a runaway.
So today, the grid will drain the power.
Right.
Intentionally.
Yeah. But like a couple of years ago, I lived in an apartment complex. There, just about 1 block away from me, there was a transformer on the pole that had a breach in it. It blew up, caught on fire, and the pole started to burn to the ground and put us in the dark for about 3.5 hours until the utility came to fix it. So, these transformers will fail, and they will, after they heat up, you get hysteresis, and then you get a huge resistance in that circuit.
If they were all made out of superconductors, there would be no such hysteresis.
It wouldn't happen. You would never get the hysteresis.
So
you need the resistance.
The lag between the input and when you get the signal from the output, right? I mean, I'm searching here to understand what it is exactly, what you guys are talking about.
It's this the way they generate the 60 hertz. Okay, so if the 60 hertz is not a pure 60 hertz, a harmonic will start in the transformer. It reacts to the capacitive of the windings and the core density, and all that will actually start to create a harmonic inside it, like a bad vibration. And that vibration,
you got 60 hertz eddy currents or spins,
right?
Spin vortices in the system.
Exactly.
At 60 hertz everywhere, but they're going to hit material objects in the system, such as the transformer, such as the wall plug, the switch,
anything
the
that's
blender,
in its proximity,
the TV, anything that's plugged. They're going to hit other devices that are not, exactly tuned to 60 hertz.
Well, that's why you got to have the circuit protection in your house, to protect your computers. The
isolation.
old isolation. All the old tube TVs from the 70s and 80s.
Filters. It's like they use capacitors to filter out the high frequencies. They use coils to filter out the low frequencies, so that way they can get you your clean 60 hertz, and anything that got in the way of getting you your 60 hertz on the way to getting to you will be removed at your house before it goes to your devices in your house, which is good for you and everybody else that's connected to the grid, because if you don't have a pure sine wave inverter to clean up the 60 hertz and remove all the dirty signals that got created by that 60 hertz bouncing off of refrigerators and other devices that are not exactly tuned to 60 hertz, so they're going to create an off-pitch frequency or even a resonant harmonic on-pitch frequency.
And if it gets bad enough, those eddy currents will just eat through the wires.
Yeah, because they self-amplify. They keep
building up, and it still happens today.
And that is evidence this over unity thing, you know, right there.
Yeah, because it's a closed circuit, it has nowhere to go. So now you got, because you got a lot of electricity going through a wire, you got a huge amount of magnetism. Magnetism can rip things apart just as easily.
I mean, it's not like the energy that came from the grid that went into a device that then slightly
Altered it, detuned the
detuned your
circuit.
60 hertz slightly,
Yep.
sent it back into the grid slightly off tuned. It's not like.
Does it create a let's call
What I'm
it
saying is it's the same signal, but it's a different tone
Right.
that's creating
It's like a badly tuned guitar. Yeah.
feedback.
Yeah, it's a feedback, like a badly tuned guitar, right?
And the feedback gets louder and louder. And if that's not clear evidence of over unity existing, it's coming from somewhere. It's not coming from the grid. The feedback is, it's coming from the devices are establishing the feedback to begin with, but the feedback is being perpetuated by something outside of the grid and everything connected to it.
Yep.
The grid and everything connected to it is establishing the sound wave on the grid.
But
once that's established,
yeah,
it's like it's like that wall again. It's like that clamp on that last pin.
Yeah.
On that video, it's like the signal is bouncing back.
It's a deflection, right?
And it keeps bouncing back and forth and getting louder and louder.
What would you call that space that this is being, looped around? Or
it's within the transformer core. It's happening in the core.
Okay.
So well, hold on. But this buildup of hysteresis inside the system, the grid or whatever device, it's trying to get out. Obviously,
that's right.
Heating up.
It's heating up and wants to get out.
It's the first evidence of it getting out of your circuit and going back away from your circuit in the form of heat, not into your circuit.
Oh yeah, they got some. There's some cool videos out there showing substations.
Some of that heat's coming from your source. Some of it's coming from the radiation byproduct of your source.
Yeah, just
through the device.
Lulu, just type in the Google search transformer substation runaways, and it'll show you the transformers blowing up. It's very violent, especially a large one.
I was searching electrical hysteresis, and I got this like bunch of images, but like the Y and X axes.
Right. Isn't it a form of entropy? Like it's all like.
It's destruction. Heat will destroy.
Like the eddy currents are all evenly going different directions or something?
Come on. Click.
Or are they all or is the hysteresis when they're all going the same way and colliding into each other?
Showing this.
Yeah. Well, it's collisions. Yeah. It's an unbalanced waveform, right?
So they're not able to go around each other anymore. They keep hitting each other.
Yeah. There's too many collisions in the
you see this
frequency.
It's right there, and it's like your Y and X axes, but it's creating a space between, I guess, the input and the output. And
so it's like a hole.
Yeah, I'm asking, like, would this be considered void space?
Yeah, it would be.
Yes. Okay. All right.
Yeah, I guess you would almost call that well, I'm not sure exactly if it's counter space, but yeah, it'll create a void
so
there.
Then you could use a magnetic field to compress eddy currents onto each other and create more hysteresis.
And well, what creates eddy currents is magnetism. So obviously, magnetism has a key part in hysteresis.
So the magnetism is not being created in the right geometry then.
Yeah, it's out of why it's just out of balance.
Geometry is compressing it's causing the eddy currents to
build up and heat up
each other, hit each other instead of going around each other.
Right, it has nowhere to go. Right, and then you get the hysteresis. The wire heats up, and that's when you get a breach and a runaway. Right.
Hey, sorry, I'll be back in 5 minutes.
Force them to heat each other by.
Yeah. Okay.
like the Hadron Collider, they use the magnetic field to force them to hit each other.
That's right. You have to
So they
confine
don't
that
go
space.
around each other; they hit each other.
Yeah. Yeah.
So that's what the magnetic field is doing in all of our grid. It's not the magnetic field is not being generated in the right geometry. Maybe
That's
the
right.
60 hertz is responsible for that geometry.
Well, definitely the magnetism is a big part of hysteresis. Yeah, that's where the magnetism actually starts.
Maybe that's why they use
working.
50 hertz. And is there? Do they have that problem with hysteresis in the East?
Oh yeah, it doesn't matter. It's a mechanical system, and there's bound to be problems, right? It's
Oh,
going
right,
to
right.
happen.
Because
It's
there's
going
always
to
going to be
happen.
some device that's just not
Sure, one of the wires wears out, or it gets too hot, or the
corrosion
canister
here and there.
or the canister that's holding the transformer, the oil leaks out.
There's
It
no way
can't.
around that.
There's no way around it. Like at my work, we actually have a substation.
There's only
right.
There's one way around it. You have your own private grid and make sure all your terminals are nice and
See,
perfect.
my work is actually on the same grid as the hospitals. All right. We actually have a substation right beside our building. It's 44,000 volts going into this transformer. The transformer is bigger than my car. That's how big the transformer is. It's like 3 of my
isolation transformer.
It's a substation. It's actually
each one of it is isolating to some degree. It's
like our
isolate.
building. Like a lot of our machines take 600 volts at like 100 amps.
You really can't isolate wireless frequency though.
No, well, unless you Faraday cage it, that's the only way you can control that. But I'm talking like I got a substation right at our work. It's right outside our building. So there's transformers like I said, it's 3 times the size of my car, and it says high voltage, 44,000 volts going into that transformer. So most of our welding machines and all our heavy equipment, I think we have like 600 and 120, 240, 350, 600. We have a whole range of different voltages. Obviously, the 600 is used all for the welding, right? So we got a lot of juice going in that friggin' building. Let's just say that.
Well, it's
200 amps.
It's a medical.
How many amps? Oh,
600 volts.
600 volts. I believe it's 200 amps.
That's what I thought.
Yeah.
You don't want to go any higher than that.
No. But because we use so much reactive power to power our
that's 12,000 watts, right? Isn't it? Or wait, 120,000 watts.
Yeah. No, we're talking high. Yeah.
That's 120,000 watts.
Yeah, they spend over 100,000 a month on electricity in this building.
Well, it's a medical, right?
It's on the medical grid. Yeah, it's part of the hospital grid.
Why do they got to pay for the electric if it's government?
No, you still have to pay the utilities. It doesn't matter.
You mean the power company's private?
Well, no, like it's on part of Ontario Hydro, right? So that's provincial. That's in our province, Ontario Hydro.
It's private.
It's controlled by the government.
It's government.
Oh. Yeah. Now the company I work for is a third party company. It's not government, right? Actually, our company is actually American.
Are there any private grids out there?
No, not in Canada. No.
What about the U.S.?
U.S. I'm not too sure, but I know in Canada there's no private grids. Maybe up in Nunavut, in the Arctic area of Canada. Maybe they
Florida, you have Florida Power and Light. I guess that's state. So that's
we have power grid going all the way up to Yellowknife and Hudson Bay. They have power
Central grid. Florida. You have Central Florida Electric Company.
Like we have nuclear power plants in Northern Ontario as well. We call the Bruce Power Plant. So at one point I was making parts for that power plant. But yeah, we got a combination, a lot of hydro and nuclear here.
I think all of the power grids in the West is government.
Oh, it's all even I imagine
the names don't make it sound like that though.
if you got, say, like a solar farm or a wind farm,
Well, read the names a little closer, you know.
yeah,
What's
they
the
could
power
be.
grid in Texas, Lulu? What's their name?
We've got Centerpoint. We've got Entergy.
The full name of Centerpoint.
I don't know. I just know it's
Is it
close.
Texas Centerpoint Electric? Something like that?
It's probably state-owned,
I don't
most
It's got a
likely.
state name to it somewhere in there.
Now, I know a lot of your power comes in from California.
Yeah, the
Texas.
second you have a private company try to provide electric, they forget about
I
it.
don't think they do. They're pretty strict about power generation in Canada as far as like the power grid.
You have to go
It's
through,
usually,
like, if you want like solar, you have to go through the state's program to,
Yeah, they already got that covered too, don't they?
solar companies you could use. You can't just like go,
It's only private in the individual scale.
Yeah. Like if I
Yeah.
wanted to put solar panels on my house, I have to use specific companies. I can't just use any, even
Not
if I
true.
find,
You could buy a solar panel from anywhere you want.
now
but-
you can now there
But
is
if you install it and it's not installed to code,
right.
they can make you take it out and have a
Yep.
licensed person put
Yep.
it in.
Exactly.
it's not
See,
Give
about
you a
the,
violation for not doing that and take your house away.
no, it's not about
That's what
the
they'll do.
installation.
No,
part.
no, it's true. They're very strict about it in Canada as well. Like if you set up a solar system in Canada, it
You
has
could do
to
it without a permit, but if it's to code,
no, it
they
has
can't make you take it down if it's to code. They have to
No,
inspect it and say
like-
it's code or not. You have to pull a permit though,
no.
No.
See, in Canada,
as an
yeah,
owner.
our law is different. It actually has to be installed by Ontario Power.
You can't pull a permit as an owner, Mike,
No, not for that. No,
for your house, your
No.
apartment.
no,
can't?
Like
no.
even the
Nope.
brand, the solar panels, if they don't approve it, you can't
Same
use it. Like
here.
example,
No, like you could use something as long as it doesn't connect to the existing grid, right? So
Right, they can't bother you for that.
right. So like my brother, for example, he lives in a rural area where it's kind of more
You
in.
can use your fridge all day long.
Yeah. So
Your,
he has
your,
the
your AC, everything. You want to plug everything into your own grid as long as nothing is connected to their grid. And if
Yeah.
anything is connected to their grid, it has to be done
by
to
them.
code
Yeah.
with the proper, registered equipment or approved
Yeah.
equipment.
That's right.
And then you can do that. Yeah.
As long as it goes by the code by Ontario Power Generation, like my brother.
I
He
hear
has
they cheat people when they try to send power back to the grid, though.
Oh yeah,
they
they screw you on that all the time.
It's like we're not even worth doing.
But in my brother's system, he has a breaker switch and a second one, which will actually detach his house from the main grid, and then he pulls the other switch and he can start his generator up. So that box there cost him $2,500 to get installed. So that will actually break the physical connection between him and the grid.
And that's like that's like a $80.
Oh yeah. Oh, they charge you huge bucks for it. $2,500.
Oh, it's like a $150 panel.
Yeah, and they charge you $2,500 to install it. Yes.
like here,
Yeah.
here in have a
Top
program
300.
that the state reimburses that if you go solar, but you have to use the solar companies that they provide you with. Why? Because it's a government contract. Some, could be because some
It's a
politician that
$2,500 switch.
makes solar panels, and they are forcing people to use these specific solar panels, and they suck. The ones that comparatively do the research, they're horrible. They break down very fast.
Yep.
They don't, but they won't cover them. Like the state won't reimburse you through your taxes if you don't use the specific ones that they allocate. So yeah, great.
Yeah. See, here's another scam in this. Yeah, here's another scam in Canada, in Ontario Power Generation. If you want to go off the grid, you want to be detached from the grid, they charge something crazy like $4,000 to detach you from the grid.
And then when you want to get reattached, it's the same thing.
Oh, it's probably more. I wouldn't doubt it for a second. It's probably more.
Just stay connected, pay a small bill or whatever.
Yeah.
That way, you can always.
It's they call it a disconnection fee.
You could use the grid to charge up your batteries. They can't
Yeah.
stop you from doing that.
Yeah, I know how to do that too, but we won't talk about that now. anyways, I'm gonna go for a quick smoke. I'll come back and then yeah, we'll go for another half hour and then we'll call it quits. I'm pretty beat. It's been a long week, but yeah,
Yeah.
carry on. I'm gonna go for a quick smoke and I'll be back.
So
Phil,
I had to go grab my nachos.
I wanted to ask you about your invention. Like, does it have to do with that Mercury motor?
Sorry.
I was asking, like, your thing that you're working on. Does it have to do with that Mercury motor that I think a few months ago you showed us? Like
Yeah, the gallium vortex.
yes, yes.
Yeah,
Oh, not Mercury. It's gallium.
yeah. I'm gonna redo it in a professional lab next month in August in a scientific lab. So there's not gonna be doubts anymore that it could be this or it could be that. That it's really working. I want to prove that it's really working because of my theory. So so we're gonna rule out all the side effects that could come out.
Okay.
Yeah.
What is in this word?
So your car battery lasts pretty long.
Phil, you there?
Your car battery is
Okay.
suffering.
Can you hear me?
Yeah.
Phil,
Yeah.
I want you to get a double pole, double throw relay and connect your power supply to the relay. And when you're ready to connect the output of the relay to the MHD and flip the polarity back and forth at a high frequency, let me know if you have any questions with that wiring. I think you should try that out. The same power supply you're using now, the same voltage and amps and everything. What are your volts and amps on that anyway? 12 or 40?
Sorry.
What are you pumping on volts into that MHD?
The volts is like 5 volts, something like that.
Oh, that's nothing. And the amps?
120 minimum.
120 amps.
Yeah. But we're gonna go to 500 amps with some battery.
Well,
So
this relay can't handle that kind of amps. But if you want to do the experiment and turn the amps down, and the volts, this relay can handle like 30, 36 volts. You can get relays that can handle a little more. But if you're willing to turn the amps down,
how do you call that again?
a double pole, double throw, DPDT.
Okay.
Double
Relay.
pole, double throw. You can use those relays to take your positive and a negative and create a plus minus minus plus back and forth at a high speed. You know what I'm saying? You can basically flip the polarity back and forth with this relay. So if you wanted to push, what was it, 200, 300 amps? If you
Yeah.
wanted to do that in the same method of flipping the polarity, then you could use the same relay to then trigger a heavier duty relay. Of course, those heavier amp relays cannot move as fast, so the frequency will be slower, but nonetheless, you can still do the experiment of reversing the polarity back and forth at a high amperage across your magnetohydrodynamic device. Now, as far as I know, nobody's tried that, but everybody has tried, both directions, one or the other, I'm sure, with the polarity. But going back and forth constantly at a high speed is a different thing. than
But
just going this way and then trying this way and not getting any results.
it's similar to an AC current.
Yeah, it is similar. And you're using DC, right? 5 volts.
Yeah.
DC. It is similar to AC. It's like it is very similar because AC has a plus and a minus, and you're reversing the polarity on the DC, kind of simulating that same concept of going plus and minus, but or creating two
But
potentials
differences. Yeah.
Now, when you have your plus and minus connected constantly to the MHD in one direction, your only two potential differences are the plus and minus, and their relations to each other on the device, and their distance and separation and all that. There's your two potential differences, the plus and minus. But if you want to increase the potential difference going on the device, if you flip the polarity back and forth, you continue to create a potential difference. You're creating the difference. By keeping the polarity one direction, plus and minus, and not changing that, that's it. That's your difference. But if you keep changing back and forth the polarity, you're creating the difference over and over again. You're actually turning the table around 180 degrees.
The gallium
in the other 180 and the other 180.
But
you're actually creating this difference.
The gallium is going to spin in one direction.
Yes. The gallium's going to go like this, and it's going to go like this. And it's going to go like this, and it's going to go like this. So you could try slow speed. I think a slower speed would be more effective than a higher speed, or maybe not. Like a higher speed, the gallium won't get enough time to build up momentum to go in one direction, but you will create these miniature flows, these quantum scale flows, because your pulse is so quick in one direction before you remove it and go the other direction. You create these miniature flows in one direction, then the other direction. Maybe the majority flow is not moving, but at a small scale, something is moving backwards and forwards really quick. Something in there has got to move backwards and forward. Even if you don't see the general mass of the liquid going backwards and forward, I don't expect you will, unless it's at a slow frequency. You would see that if you keep the contact down longer. You'll see it go one direction and let go and flip the polarity. It'll go the other direction. That's all in your duty cycle and your timing on the contact.
Yeah.
That's about right there. That you'll see like flow that way, 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 flow that way. Clockwise, counterclockwise. Now, would that get you the effect you're looking for? I don't know. You want it to go in one direction at a high speed, obviously, to create the vortexual lift. Or whatever, the centrifugal effect. I get it, but I'm just saying it's a good experiment to try.
I'll try it.
It's not a hard one to do.
Yeah, I'll try it after I'm done with my primary experiment.
I think the more differential you could create, the better. And by flipping the polarity backwards and forwards quickly, you're creating a very intense difference in the potentials.
Yeah,
that's not obvious.
What would you use to do that? Like
flip the polarity back and forth.
Okay,
you're screwing around with the potentials. Like the potentials don't know which way you want to go. What they do, because they can move at the speed of light, right? So they do know which way you want to go. Every time you switch the direction, they're going to switch too. Flip the polarities backwards and forwards, back and forth. Plus and minus, minus and plus and minus on the coil or on the MHD or whatever device. You're creating a left-right turn like that, like a wiggle.
No, I'm understanding that part. I'm just trying to think of what would be that mechanism that could do it that fast. Like
flipping the polarity on the coil.
Okay.
Yeah, no, I think what she's saying is what you actually use to make that flip.
The double pull, double throw relay.
A
I'm
double
sorry,
pull.
I didn't get you. The relay does that.
Okay.
Hold up. I made a video that demonstrates exactly what I'm talking about.
Yeah, I have actually a switch that is a double pull, double throw.
There. Huh? Oh. Okay, I'll explain here what's going on. Ask me any questions you have about what's going on here, the colors and all that. I'll explain what the colors are, you know. The green is negative, the red is positive. And you can see the relay on the right. And you see the top two colors, the red and green?
Yeah.
How they change back and forth?
Yeah.
Okay, so the number 5 and 6 pin, red and green, is always got color, right?
Yeah.
The pin 5 and 6. 6 is red, 5 is green.
Yeah.
One up from
Okay.
the bottom. 7 and 8 are at the bottom. 5 and 6
Alright.
are up. They're always got color, right? They never turn off, right? Because that's where you give your voltage permanently.
Yeah, you're just redirecting the power.
And 7 and 8, when you give voltage there, it activates the switch to go to the left. When there's no power on 7 and 8, it's black. There's no color, no green and red. And the switch is by default to the right. And giving pin 5 and 6 to pins 1 and 2 in such a way. I'll pause it. Where's the pause? Pause. Okay, now you see how pin 6 is touching pin 4?
Yeah.
And
Yeah.
moving, and I got pin 1 and 4 connected with a wire.
Yeah.
Now, on the left side, the left switch, it's not doing anything with pin 1 at that moment. It's doing only with pin 3. See, pin 5 is sending negative to pin 3 on the left. Pin 6 is sending positive to pin 4 on the right. So when the two switches flip to the left, pin 6 sends positive to pin 4, and pin 5 sends negative to pin 3. Therefore, having the wires connected as they are here, drawn, pin 3 is connected to pin 2, pin 4 is connected to pin 1, and this is the end result. You'd be able to flip the polarity like that at whatever frequency this relay can go.
Yeah.
And by wiring it like this. Now you can wire this relay in another way that can operate another circuit that I've got drawn out to run 2 coils.
Yeah, we're gonna square up here in
one, two,
a couple of minutes, guys. So if you want to get one last word in, I'm getting pretty tired here. I'm starting to fade.
So now it's touching to the right.
Yeah, that's cool.
I will wire my 2-way cord, and I'll show it to you. Let's see. Yeah.
You see now pin 6 is sending positive to pin 2 instead of positive to pin 4. You see that? The pin 6 is sending red to pin 2 instead of to pin 4 because the relay switched to the right.
Yeah.
And then when it switches to the left.
What system are you actually working on right now, Mike?
It's a little confusing, but it's there. This right here is very where I'm ending up with. I have to actually build the 2 coils 90 degrees apart with the 2 180-degree rotor magnets and bounce the flyback between the 2 batteries back and forth.
Are you still working with the Newman device, or?
Yeah, that's already done, and I just want to make a stator for it that's appropriate, and then test it out again.
Now Newman used analog, or basically like a stator.
I'm using this to run that motor.
Yeah.
This method of triggering to run that motor is going to push the north-south magnet twice every 360 degrees. So in 180 degrees, it pushes the north and the south with two hands, and the
Right.
other 180 degrees, it pushes it again, the north and south with two hands, by flipping the polarity every 180 degrees.
Right. Cool. Right on.
That's how that one is running now, and it works fine. And there's no free spinning for 180. It's there is no free spin in the in it's always receiving a push.
Yeah. Anyways, guys, I'm
Polarity.
gonna go ahead, Lulu.
No, I was saying now, like, because I've tried playing with magnets, what Mike was doing. You know how his little round magnet was doing this, but I could not get it to, constantly go in motion. But I think because I didn't connect it to flip the polarity. That's what's giving it that extra push to do the
Yeah.
rotation. No, okay, I understand. Okay.
Yeah, you're mechanically creating that
Yeah.
spinning. Yeah.
I was hoping naturally to keep, to add maybe an extra piece of weight on one, like a little bit where it gives it that rotation. But okay, yeah.
Yeah, he's just using a different method. A lot of people just do the single pulse that would create,
Well,
the spin 360 degrees and then
Yeah.
create the next pulse to push it again.
But you want to be able to not, add energy. You want it to do it, by itself, like,
Right.
like not pumping it with anything else, like
Yeah.
it on its own. And
When
well,
you get,
one note about that setup, I did have to trigger one side a little longer than the other to get it to run smooth.
yeah.
Because and I figure that's because the north is stronger and the south is weak.
Yeah.
So,
Anyways, I think we're gonna square it up here. I do have to go. I'm like fading fast here, so yeah, we go live again next Friday night at 9 o'clock Eastern, right here at Faraday Research. Thanks a lot, everybody. Thanks to my panel. Lulu, take care of yourself. Hopefully, you get your power back soon,
thank you. I
and
hope so.
hopefully everything works out for you there. All right, guys. Thanks a lot, and we'll see everybody next week.
See you next week. Good night.
Take care.
there
Take
it
care.
is.
Take care.